some of the important things that we try to bring out regarding the MSK waveform, regarding the MSK modulation scheme are the following. First, it uses a cosinusoidal pulse shape, right, instead of actually a half cosine pulse shape instead of a rectangular pulse shape. Second, because the I and Q channels use the cosine and sine pulse shapes respectively, half cosine and half sine pulse shapes respectively, it turns out that the final modulated waveform, which is the sum of the I and Q waveforms, has a constant envelope, right. Third, the phase changes now don't occur abruptly in this waveform, they occur continuously over the entire bit interval, right, and it is therefore similar to offset QPSK signal in that every TB seconds, every T sub e seconds you have a phase shift of pi by 2, but that phase shift is gradual rather than abrupt. So there are no sudden phase transitions. In fact, because you have continuous phase transitions, you can also think of an MSK signal as some kind of a FSK signal, because you find that in every bit interval you can interpret its instantaneous frequency to be either FC minus 1 by 4 TB or FC plus 1 by 4 TB, right, and therefore that brings us to the last property that we were trying to complete last time but could not do so. We will now take that up, the FSK interpretation of MSK. That is what you wanted to discuss, right?
So the graph, the spectral density which we have got.
Yes.
That particular graph. And sir, why do we want to have a smooth variation of the phase? I mean, you explained this before, but could you just once again?
I don't have the spectral graph there with me. But what is the difficulty with that?
I mean, how do you get that comparison? How do you get the various graphs?
Oh, how do I get the various graphs?
Yeah, for instance, you gave some formula for SF for MSK also.
Yes. I have not gone to the details of spectral calculation of MSK, right? Because that's a bit involved, and I think it's outside the scope of our discussion.
So, secondly, why do we want to have a gradual phase change? I mean, do you explain this before?
Yes. Okay.
Why not say in OQPSK as you have abrupt?
The QPSK and OQPSK and MSK, you can think of these three as some kind of hierarchical improvement of every waveform instead of the previous one. The improvement is in QPSK, normal QPSK, you have a 4-phase constellation, and every symbol interval or after every pair of bit intervals, right, you have to you may have a phase transition of either 0 degree or 90 degree or 270 degree or 180 degree, whatever, right. So these are the possible. In other words, you can have phase transitions of 0 degree plus minus 90 degree and plus minus 180 degrees. The plus minus 180 degree phase shifts are rather large, right. Similarly, in the offset QPSK, you will have phase transitions more often. They will be now distributed every bit interval rather than every 2 bit intervals, but the extent of the transitions will be only going up to plus minus 90 degrees. The magnitude of discontinuities will be smaller, right. And thirdly, in MSK you have no phase discontinuity at all. It is in fact what is called a continuous phase waveform, right. In fact, the FSK that we have also said that MSK can be regarded as a FSK waveform. It is an FSK waveform with a special feature that it is a continuous phase FSK signal, right. Now, why the advantage? That is a question that Dipankar has asked. You can appreciate that if a waveform contains a lot of discontinuities, it will have larger extent in spectral domain. That is reasonably intuitively clear, that if you have a discontinuous waveform in time, it will have a larger energy distributed at higher frequencies in the frequency domain, right. Therefore, if you try to band limit such a waveform, you will expect more distortion in this waveform than if you try to band limit a waveform which does not have such discontinuities in time domain. This is intuitively clear, right? Because in a continuous waveform, most of the energy will be concentrated in a narrow region, whereas in a discretely discontinuous waveform at several points along its locations in the time, you will have significant energy at higher frequencies, which will be cut off by the filter, and because it has been cut off, the waveform will be highly distorted. The form of this distortion for phase discontinuous waveforms will be that your amplitude of the waveform will no longer be constant, it will go through amplitude and phase fluctuations. Well, amplitude fluctuations are a serious thing in systems where there are non-linearities, right? Because if you are going to go through a large dynamic range of amplitude fluctuations, that means all the components of your communication system, maybe receiver or maybe transmitter, must operate in a linear fashion over this entire dynamic range of operation, whether it's a low amplitude at times or high amplitude at times. Now it is very difficult at very high frequencies like microwaves or even higher frequencies to design such linear amplifiers or linear power modulators, right? Typically they will have a nominally linear region of operation around a fixed amplitude point, right? And if your amplitude fluctuation occurs outside that region, then you are bound to encounter the further distortions due to non-linearities, and those distortions are much more severe and much more difficult to eliminate than if you were to take care of it right in the first instance, right? Because do you know what kind of distortions are introduced by non-linearities? Typically harmonics, intermodulation terms. That is, for every frequency that you may have, you will have every set of frequencies that you may have, you will have at the output other frequencies generated. New frequencies will get generated in the system which were not present in the input waveform at all, which will further spread the spectrum, right? So it's going to be very bad for the communication system as a whole, because it may further introduce what we call spectral leakage into other channels, because it will be generating frequency components which may lie in the frequency band of operation of another receiver close by, right, which you won't like to do. So therefore it is preferable to use waveforms which have constant envelope or constant amplitude, and MSK waveform satisfies that requirement. Does that answer your question, Deepankar? Okay. So we will proceed from this point onwards. What we have seen is that we can also interpret MSK waveform as an FSK waveform. So look at MSK as FSK. In fact, the name MSK, minimum shift keying, comes from its relationship with frequency shift keying, right? We have seen that we can think of the two frequencies, the waveform having two frequencies, f1 and f2, corresponding to f sub c minus 1 by 4 t sub b and fc plus 1 by 4, or other way around. I don't know how I defined them last time. This could be plus, this could be minus, or vice versa. Now what is the frequency separation between these two?
1 by 2 dB.
1 by 2 dB is the frequency separation between the two frequencies, right? Now it can be shown that this is a minimum separation between two cosinusoidal or sinusoidal waveforms which will be mutually orthogonal. Mutually orthogonal. That is, if you take two sinusoids or cosinusoids of period 2 TB, right, or period TB, sorry, bit interval, then this is a minimum separation that is required so that these two sinusoids or these two cosinusoids are mutually orthogonal over this interval, not over minus infinity to plus infinity, over 0 to TB, right?
Sir, the statement is still not clear.
Okay, suppose you are interested in finding out cosine omega 1t, cosine omega, there are two pulses with carrier omega 1 and carrier omega 2, and pulse durations are each dB. We want to find out whether these two waveforms are orthogonal or not, or what will be the condition for omega 1 and omega 2 which they should satisfy such that this is 0. Right? Suppose we ask ourselves this question. We realize that f2 minus f1 should be a multiple of 1 by 2 TB, right? And 1 by 2 TB is the minimum possible separation for which this will be true. That is the reason we call it minimum shift keying. That is generation of an orthogonal pair of waveforms with a minimum frequency shift between the two, right? That's where the name is derived from. It is derived from its similarity to an FSK waveform, and since the corresponding FSK waveform is orthogonal with the minimum possible shift in the two frequencies, we call it minimum shift keying. Clear? Okay. If we have this interpretation of the waveform, this also tells us that we could possibly have generated an MSK like waveform or MSK waveform strictly speaking by directly mapping the incoming zeros and ones onto frequencies. So far, how did we view the MSK waveform? We said we'll take the incoming bit stream, it may be some arbitrary bit stream, right, and you are splitting it up into two bit streams, I and Q bit streams of each having a rate of half of the incoming bit stream, right. So for example, all even bits would go to, all odd bits will go here and all even bits will go here, sorry, and so on. And then each of these was modulating, was using a half cosine pulse here and a half sine pulse here, right? Sorry, other way around perhaps. Yeah, that's fine if you take this as 0. This was, I'm sorry, if this is a common reference point. So this was using a half cosine pulse and this is using a half sine pulse, right? And then further modulating the carrier and then the two were being added up, right? That is how things were being done now. So this was a modulation process. This was the way we were mapping our incoming bit stream onto finally an MSK waveform. I have not drawn the complete diagram because that's quite obvious. If you want, maybe we can do that. Maybe we can quickly do that. You have an incoming data stream, split it into two, multiply with cosine, what was it, pi t upon 2 TB and sine pi t upon 2 TB, right? Then we were multiplying with the carrier, cosine 2, sorry, this should be sine here, sine 2 pi f naught t, this would be cosine 2 pi f naught t, and then you are simply adding them up or subtracting whatever. Alright, this is your MSK waveform. This is how we have been viewing the MSK waveform generation so far, as offset QPSK waveform, right? These are the I and Q bit streams which are mutually offset with respect to each other by 1 bit interval. This bit stream is modulating, it should have been Q and I this way because I have taken the cosine over here. This is modulating this is being shaped by a cosine pulse, this is being shaped by a sine pulse, right? And then we are introducing the carrier, right, and adding them up. This is how the offset QPSK waveform would be generated, and this is how MSK waveform would be generated. The only difference between this and offset QPSK would be that offset would be using a rectangular pulse here and same rectangular pulse here with a shift of half bit interval, half symbol interval or 1 bit interval, right? So this is how we have viewed the MSK generation so far. What I am now suggesting is that since we can view the frequency of MSK waveform to be either f1 or f2 in every bit interval, we could have directly generated an MSK waveform which could perhaps be different from this waveform that we have generated here by directly mapping the incoming ones and zeros onto frequencies, keeping the phase continuous at every transition of bit, every bit transition. That is to say, instead of thinking of it shaping the I and Q pulses like deciding the I and Q pulse pattern in this fashion, we could have directly looked at the phase function. In let's say corresponding to 0 we have an increasing higher frequency, and corresponding to 1 we have a lower frequency, just for the sake of argument. That means for every incoming 0 I could increase the frequency to f1 so that you have an increasing phase in that interval, or you would be decreasing the frequency to f2, right. You are changing the frequency either to f1 or f2 in every bit interval. You have one of these two frequencies present in every bit interval, and this could be done by a direct mapping of incoming zeros and ones, say a 0 going to f1 and a 1 going to f2. So I have a different modulator here. The modulator now consists of essentially as an FSK modulator. Alright, the incoming zeros and ones directly map these bits onto frequencies, onto a waveform which generates either f1 or f2 for 0, for 1, right. And if f1 and f2 are selected to be the same as we discussed earlier, fc minus 1 by 4 TB and fc plus 1 by 4 TB, qualitatively we will not be able to see any difference between this waveform and the one which we have generated using this method, qualitatively. That is, if you just look at the waveform every bit interval, you will find the frequency to be fc minus 1 by 4 TB or fc plus 1 by 4 TB. Qualitatively we will not be able to make out any difference between the two waveforms. Is this point clear? Yes.
Okay, we said that it's equivalent to the frequency shift of plus minus 1 by 4 TB in
Right.
either direction. But there we encountered 4 levels, the plus, cosine, and plus minus.
But there's 4 levels for every pair of bit intervals. This is going to be happening.
From this it appears as if it depends, the instantaneous frequency depends on just one bit instead of a pair of bits.
So we can either regard it as a binary FSK waveform or as an offset QPSK waveform. If you regard it as an offset QPSK waveform, you look at pair of bits and do that mapping in this manner. If you view it as an FSK waveform, you can generate such a waveform by directly mapping every bit onto a frequency. In that case, it would be a binary FSK waveform.
But
So the two would be
equivalent to the MSK being generated by that scheme.
this is the point which I wanted to discuss in detail. It will be equivalent to the extent that the properties of the waveform are the same, but the specific waveform that will be generated here by the same sequence will not necessarily be the same waveform that is generated by this kind of a mapping, right. That is, the specific sequence of f1 and f2 that you will get may be different here and may be different here, right, corresponding to the same identical input bit pattern. You will have two waveforms which are qualitatively similar but different in detail. That is, if you look at the corresponding bit interval and the frequencies of the corresponding bit intervals, they may not correspond to each other.
Only the mapping scheme is different.
Only one can do the mapping either this way or that way. That means if I modulate the waveform like this, I cannot demodulate it like this, or if I modulate it like this, I cannot demodulate it corresponding to the demodulator of this kind of a mapping. This is the point to appreciate.
So only thing will be that the bits will be a bit delayed.
No, they will be different. I mean, you will have to work that out. You will require a precoder if you want to do that, right? If, for example, you want to map the waveform like this and demodulate it as if it was an FSK waveform, you will require a post decoder operation, right?
That also can be done.
Whereas some kind of a transformation will be required on the bit sequence. Similarly, if you modulate it using the FSK strategy and want to demodulate it using the inverse of this strategy, you will require a precoder before you do the modulation here, right?
So can we do, sir, we do demodulate BFSK as the MSK as BFSK? This one OQPSK as
Yes,
BFSK.
we can, provided we
Data
have
level we can do this.
provided we have appropriate pre-coding or post-coding operations, which will carry out the necessary equivalence operations in the bit sequences.
So
Okay?
just to understand one thing, previously
Let me complete this discussion, then I'll come back to your question. So what I'm really saying is,
Sir,
yes,
please show this again, the last one.
this one.
Yes, sir.
All right. You have any question about it? Any question about this? This theta t comes from where? You tell me. I showed you a phase trellis diagram last time for the MSK. So basically, this is one possible path on the phase trellis, right? Depending on whether you have a 0 in a particular interval or a 1, my phase is either continuously increasing or continuously decreasing. I could have mapped it the other way around also. I could have mapped a 1 to a continuous increase and a 0 to a continuous decrease, right? So this is an interpretation of MSK waveform by direct mapping of bits onto frequencies, right? But you will, in fact, this waveform very clearly illustrates. If I do the mapping like this, the bit sequence that we have is 0 1 1 1 0 0 0 0 1. Whereas if you do the mapping like this and to generate the same MSK waveform, the bit sequence will be 0 0 0 1 1 1 0 0 1 0. This is what I have tried to illustrate in this picture, and the two bit sequences are different. What I am trying to convey by this picture is that doing the IQ or offset QPSK like modulation using this bit sequence or doing the FSK kind of modulation using this shown bit sequence will generate precisely the same MSK waveform, right? Now this is not obvious, this I have worked out, this I have worked out for you, alright. What I want to illustrate is that the two bit patterns are different. This is what I want to illustrate to you. That is, you have a different bit pattern here and a different bit pattern here. So that if you modulate using this waveform and demodulate using this strategy, you will get a wrong answer, wrong demodulated sequence. You will have to reinterpret that modulation sequence or retransform it so that it is the same as this. Similarly, if you want to modulate using this strategy and demodulate using this, you will have to again do the same kind of post decoding operation, or you have to do a pre-coding operation.
So in this case, the output waveform will be the same.
In this waveform and this waveform will be the same. In fact, this is a phase trellis. This is a phase trellis corresponding to this MSK strategy. Okay, this you can work out. In fact, one can work out very precisely what this relationship should be, and I want you to try to work that out yourself, and see if you can do it. Precisely what, but let me define the question.
MSK is sort of a differential type of thing, because it will depend, demodulation will depend upon the phase, previous phase.
Yes, there are phase relations.
Because in
That is what is indicated by this phase trellis, right? Okay, you think about it. I'll define the question more precisely for you. What I'm really saying is that if you have some binary data coming in and you have generated the MSK waveform using the INQ strategy, right? That is using the offset QPSK kind of strategy, and you for some reason want to use an FSK demodulator for decoding a bit sequence. You can do so provided you follow it up with a post coder, a post transformer, that is of post decoding transformation. Alternatively, you can have the same binary data first processed by a precoder, converted to a different bit sequence, use the FSK strategy for modulation to generate the MSK waveform, and now demodulate by the I and Q demodulator, right. Now what precisely should be this precoder or what precisely should be this postcoder is what I am asking you to try to work out for yourself as to what should be the relationship between the bit pattern here and the bit pattern here, so that you can do the postcoding operation, or the bit pattern here and the bit pattern here, so that you can do the precoding operation, right. That is the exercise I am giving to you to work out. Is it clear? It's going to be fairly simple to work out. In case you can't work out, let me know, I'll help you on that. Okay. Can we proceed further?
This precoder will require memory.
One question. He wants to see the previous diagram for theta t. Yes, here it is.
I just want to note it down. I will analyze it.
Okay. Yes, Varun, what is your question?
Sir, will it be a combination circuit or will it require memory?
That is something you should work out, no? Just think about it. Don't think about it now. Think about it later at home at leisure. Let's proceed further. And I'll now like to discuss passband waveforms for memory signaling. That is, as far as we are going to discuss about MSK waveform, we will return to MSK and all other modulation schemes that we discussed so far are going to discuss now when we talk about demodulation, right? Because demodulation I want to discuss in a unified manner rather than individually for every scheme, right? It's possible to do that to some extent. So to complete our discussion on binary, to complete our discussion on digital modulations, remember what is the hierarchy of approach we have followed. We have talked about first baseband modulations, both of the binary as well as the memory kind. Then we are discussing the passband modulations. So far we have discussed mainly the binary modulations, although QPSK and offset QPSK have come in rather surreptitiously over there, and we will now like to do a formal discussion about memory waveforms, memory passband waveforms. Again, we can classify them into two types corresponding to the situations when there is no bandwidth constraint and case 2 where there is a bandwidth constraint, in which case we typically use multi-level signaling for narrow bandwidth systems. So we will take each of these two separately. Am I going too quickly for you?
Yes, sir.
Alright, let me slow down. Now, let's do the discussion more or less in the same framework. That this is precisely the framework we did use when we were discussing memory baseband modulations. And if you remember, to discuss memory baseband modulations, the basic strategy that we used was to first define orthogonal set of waveforms, and from that orthogonal set, particularly for the case when there is no bandwidth constraint, right? And from that basic orthogonal set we could derive other kinds of modulation schemes like simplex and like biorthogonal and other things, right? This is the approach we followed there. So basically one has to talk about the orthogonal signaling set as the most important class of signaling set here, because from that basic orthogonal signaling set one can obtain other classes, namely the simplex or any other kind. Now therefore, considering case 1 first, let us mainly emphasize on the orthogonal passband waveforms, right? So, Emery orthogonal passband waveforms. Similarly, we could talk about Emery simplex passband waveforms. In fact, one can obtain Emery passband waveforms by taking a corresponding baseband waveform and simply putting onto a carrier. That's all one has to really do. So basically, suppose SMT m equal to 0, 1 to m minus 1 is an orthogonal baseband family of waveforms, right? So let this be an orthogonal baseband family. You understand what it means? That is, you are going to use a dictionary of m waveforms, and the way you are going to do the mapping, we are going to return to this question again, is you will take k bits at a time, where 2 to the power k is equal to m, right, and assign one of these waveforms to every k bit sequence, right, and these m waveforms are selected in such a way that they are mutually orthogonal. This is a set of baseband orthogonal waveforms. One can easily obtain a set of passband orthogonal waveforms by simply putting each of these waveforms onto a carrier. For example, this set of waveforms will be, then this will be an orthogonal passband family. Okay. This is very easy to check. In fact, we can generalize this, and let me take the general case first. Is it too quick? All right, here it is again. If you are not copied it, that's the problem with a monitor based instruction. On a blackboard, the thing stays there for you to keep on copying. Okay. More generally, I can take SMT now. I'm taking a situation where our baseband orthogonal waveform could be complex. Okay, so it has a real part and an imaginary part. This is a more general form of an orthogonal set of passband waveforms, which we can write in complex form as follows. So the more general statement is that if I have a complex baseband waveform, a complex family of baseband waveforms, which is an orthogonal family, then from there I can construct a orthogonal passband family using this kind of approach, right? Of course, as special cases, we could have one or both of these either of these components 0, or we may not have both of them 0. Either situation is likely. The result, which is very easy to verify and I like you to prove to yourself, is that given that these waveforms are orthogonal, given that the corresponding complex based on representations are orthogonal,
The complex representation is also orthogonal.
it has to be orthogonal for this to be orthogonal, right? The question, in fact, that is the result I would like you to prove. Given that these are orthogonal, you can show that these will also be orthogonal. If these are given to be orthogonal, this is our starting point. We start with a baseband family of orthogonal signals, right? For m going from 0 to m minus 1. Alright? See, before this, I considered the real case. I started with a real family of baseband orthogonal waveforms and suggested that one could construct a corresponding passband family using this operation. Now I am generalizing this statement and saying that if we start with a complex family of orthogonal baseband waveforms, we can obtain a corresponding passband family using this kind of a transformation, right? This is what I am saying. So this is a more general statement corresponding to the previous one that we just discussed, and therefore this is what I would like you to prove, that is the passband waveforms say SMT and S sub m prime t corresponding to two different indices, m and m prime, are orthogonal, that is SMT, these are real waveforms, isn't it? SMT, these are the passband waveforms. That is, this integral is 0 if, of course, one can write a very strict statement, if and only if kind of thing, if and only if the corresponding baseband waveforms, if you have not copied, I will just show it to you again. Okay. These two are orthogonal if these two are orthogonal. Okay, very simple to prove. Simple trigonometric identities are all that you need to use, and I like you to, or going from, you start from there, substitute this in terms of the passband representation, and you will get the answer in actually one line. Almost in one line you can prove the thing. So I would like to leave that also as an exercise for you to do, to show that this result is indeed true. Now let me try to make you appreciate this point. I think I have tried to emphasize earlier the significance of orthogonality in the context of digital modulation schemes. The significance is related essentially to the fact that the way we carry out the demodulation, so called optimum demodulation of a waveform, requires you to basically correlate a waveform with its replica at the receiver, right? Suppose you transmit a particular waveform in a particular bit interval or a symbol interval, and you are trying to demodulate it or detect what symbol was transmitted. The optimum processor happens to be what is called either a matched filter receiver or a correlator receiver, right? A matched filter receiver, I will tell you what it does, although we will discuss it in detail later. A matched filter receiver essentially will take the incoming waveform RT and pass it through a filter whose impulse response is, suppose you are trying to see whether this particular waveform is present or not, SMT, right? Then you will pass it through a filter whose impulse response is SM minus T. Well, I have taken that T to be 0 if you already know about it, but in general let me just say this much at the moment, that this will be essentially what a matched filter will be doing. and then you will be looking at the peak of this output, right? You will be looking at the, because typically these are pulses, SMT is a pulse, right? I know because this concept is further down the time. I'm just trying to motivate where this correlation operation comes from, right?
So you said it's a match filter type of thing.
Yes. This what is this? This convolution. What is this convolution? This will be R tau
ST plus tau. ST plus tau.
T plus tau or something. Well, it doesn't matter. Sn, right? D tau.
Yeah.
Right? And if you put tau equal to 0, there is something wrong. This will be. That's why I wanted to avoid this other movement. This may not be the right expression. How will you express this convolution integral?
Minus t minus tau.
Minus t plus tau.
Minus t minus tau.
Minus t minus tau. Right?
It has to be minus tau.
Okay, please. It doesn't matter. It doesn't matter whether what is the correct expression. There is
Minus t plus tau.
please. It's very easy to interpret. It doesn't matter whether this is right or wrong. We can still get to the point that I want to make. Suppose I want to look at this waveform, the peak of this waveform. It can be shown that the peak of this waveform for finite duration pulses will occur in this case for t equal to 0. Okay, this output will peak at t equal. This is going to be a function of time, right? Function
So
of t.
R tau is also of the form of those sinusoids. Can you?
It is going to be the same signal, but it is in noise.
It could be any one of these SM.
But
It could be any one of
Right
these.
now we're taking only one particular variable.
Then,
Quite true. Quite true.
so then the peaking doesn't have to occur at 0. I mean.
Yes, yes. You not let me complete my statement.
Okay.
If I have completed my statement, then you will not have this question. If R tau contains the signal SMT, right, maybe in white Gaussian noise, then this signal will peak at t equal to 0, right? If it contains a different signal at, let's say it contains SM prime t rather than SMT, then it produces 0 output, provided they are orthogonal signals. Okay?
I can't get it.
No. Okay. Suppose, let's say there is no noise, right? Then what is this waveform? This will be SMT convolved with SM minus t, right? And at t equal to 0, what will be the output? Essentially,
SM squared.
the energy of the signal, right? It will peak there.
Fine.
Similarly, if both are m primes, it will peak there.
Fine.
But if one is m and the other is m prime, right? Provided your original signals to start with the orthogonal, this will turn out to be 0 at t equal to 0. That's the significance of the orthogonal operation. I have illustrated this in this picture here for your convenience. This shows here the convolution of SMT with itself, with SM star minus, with its match filter impulse response, right? The convolution of SM prime t with its corresponding match filter impulse response. This peaks at t equal to 0. This is t equal to 0. This also peaks at t equal to 0, right? Whereas if you pass SMT through a filter which is matched to HM prime, right? At t equal to 0, you are going to get a 0 output.
But why do we take SM of minus t? Because as well take SM of t.
Well, that has to do with the match filter derivation, which we'll discuss later, right?
So this M and M prime represent members of the orthogonal family.
Right.
Okay.
So therefore, now you can think of the receiver as consisting of a number of match filters, right?
Corresponding to
One corresponding to each different member of the orthogonal family, each producing a response, and the correct filter will produce the peak at the right point.
Fine.
Right? That's the motivation for defining these orthogonal families. Right? You can easily distinguish different signals of different members of an orthogonal family through the use of corresponding match filters. Okay, this was just to motivate as to where all this comes from. Otherwise, we will be taking up these things in detail when we discuss the demodulation of these waveforms. All right. So don't worry too much about where this minus t comes from and whether this should be minus t plus tau or plus t plus tau. We'll discuss all that in detail correctly. Is it okay? You have any questions about it? What I'm basically trying to convey to you that orthogonal family of signals is a very basic family of signals, both from the point of view of the fact that it is easily distinguishable, that is one member of the family is easily distinguishable from the other members through match filter kind of receivers. Also because starting from this basic orthogonal family, one can derive a whole lot of other families, particularly the important class of simplex and biorthogonal signals, right, which are also easily distinguishable. Right? In fact, some of them may give better performance than the orthogonal family for a finite alphabet. Although it can be shown that for very large alphabet sizes, where m is very large, the orthogonal family is in fact the optimum family to use in some sense. But those are things which we cannot discuss here. Alright, let's return to further discussion of this. How much more time I have? 5 minutes. Okay, that's okay. So how we are going to map bit sequences to these waveforms? We are going to choose an value of m which is the power of 2, let's say 2 to the power k. So basically we are going to organize our incoming bit stream into segments of length k bits or words of length k bits.
So we are still talking of the receiver, match filter receiver.
No, I am now coming back to the orthogonal family of signals, right? That discussion is over. So data is segmented into k bit words, right? And nth such word, let me denote that by m sub l. M sub l also can take the value either 0 or 1 or up to m minus 1, right? But L refers to the fact that this is the first block of k words, this is the next block of k words, right? So we are now talking about the nth block of k words. Each of this could take any of these m values. This m sub l can take the value from 0 to m minus 1. So this is mapped into a waveform, a passband waveform Sm sub lt. Alright. Therefore your overall transmitted waveform is Ct, which is going to be the sum of all these waveforms. This waveform is transmitted every, suppose this interval is t seconds, right, from one block of L symbols, L bits to the next block of L bits, right. So every t seconds you will be transmitting a new such waveform, right. So SML t minus LT. This corresponds to L.
This could be LKTB.
Yes, you could write t equal to KT.
NKTB.
No, capital T would be
T is equal to
KT, right? L goes from whatever. Fine?
So multiplied by some.
No, I have said that M sub L is mapped into this waveform, whatever the waveform is.
Aren't we discussing passband?
Yes,
अच्छा ठीक.
this passband.
SMLT.
SMLT represents the MNth passband waveform corresponding to this particular word that you have, right? Fine. Let me take one example just to finish this discussion. So we'll take an example of an orthogonal family. Let me start with following 4 sequences in a base pair. A0 is the sequence, complex sequence 1J 1J. A1 is similarly 1J minus 1 minus J. A2 is 1 minus J minus 1 J, and A3 is okay. You can satisfy yourself that these 4 complex sequences that I have written down here are indeed orthogonal sequences. That is, if you take any pair of sequences and compute this sum, you will find that to be 0, where ML could be, for example, this should be M prime L, where ML prime or M prime sub L is different from M sub L. So if I choose the same M and M prime to be same, of course, then this will not be 0, then it will be obviously equal to 4. Oh, no, not 4. How much will it be? 1 square minus 1. It will be 0.
What do you mean by the conjugate?
It is 0 in 0 for all situations. Yes. Yes. Whenever you have complex waveforms, the orthogonality is defined in terms of a conjugation operation. Remember,
Yes, sir, that's true.
Right?
How do you do it in the case of 4 arguments, 4 parameters? So could you just illustrate?
all right.
for
Let's
A1,
take one of them.
A1,
Let's take
A2.
this pair.
Okay.
Right.
Yeah.
You basically multiply on a bit by bit basis. Right. 1. This will be minus 1. This will be
Minus 1.
minus 1.
Taking the conjugate.
Oh, I'm sorry. This will be minus 1. Yes.
Minus
So
J
who-
will become plus 1.
This will become 1 plus 1
2
minus 1,
and then minus 1 again. 0.
then minus 1 again. So the result is 0. Okay. 1 plus 1 minus 1, and this will become plus j. So it will become
It will be 4 for the.
It will be 0 for the.
I think it should have been 4.
It should be 4. That is 4.
I was in fact a bit confused. Yes, because you have to conjugate that also, no? So it will become 4. So this is true for ML not equal to ML prime, right? So suppose you have this sequence of length 4 or 4 sequences, then I can now define 4 waveforms.
So
That's
what are
40.
these 4 sequences? These are basis.
Yeah, how do you.
I'll come to that.
Correlated with the SML teacher.
For example, see, you have decided to use. I want to define 4. I want to define 4 waveforms, right? Basically, 4 orthogonal waveforms is what I want to define. Therefore, I should take 2 bits. Right? These 2 bits are mapping onto one of these 4 sequences. I can do that.
But
So
those 4 sequences would be 1j.
due to the
So 1j,
waveform,
1 minus j.
You could think of this as if you have rectangular pulses with,
Sir, but why the size is 4 of this sequence? It could have been 2 because if you.
Yeah, then.
Because 1j, 1 minus j1 and.
Yeah. So you could have had.
These could be complex numbers as well. That is besides the point. But what does it do to the waveform? Like,
I have not fully defined the mapping yet. If you let me define the mapping, I think things will become somewhat clearer. Let's go through the complete operation. The 4 waveforms that I am going to define from this sequence are the following. ST. I mean, this is just an example. It doesn't have to be done this way.
where ST is cosine something.
Where ST is any elementary pulse which satisfies certain properties, right? We'll talk about that in a minute. And so on. Right? You can similarly define S2 and S3. I think the mapping is obvious how we are doing it. So basically what we have done is we have taken a pulse shape ST, right, and from that basic pulse shape I have generated 4 waveforms which are mutually orthogonal, right. Now these are of course baseband waveforms, right. To go from here to passband waveforms you will translate into real imaginary parts, and
These are baseband because we still haven't introduced carrier.
we haven't introduced the carrier.
So this S in itself could be a passband waveform because it's not defined as.
I am going through the steps that will correspond to the way I have defined my orthogonal family, right?
The passband
The
waveform
orthogonal
cannot be-
family, I said, could be orthogonal passband family could be obtained by deriving it from a corresponding orthogonal baseband family, right? So first I have constructed an orthogonal baseband family for you, right? And then from there you go to an orthogonal passband family. Now how you allocate bits to waveforms is up to us now. You have 4 waveforms and we may allocate up to 2 bits in any way you like. Obviously this is not a very nice thing to do with the way I have done it, right? Because it will occupy a total interval of up to 40, right?
40.
Whereas we are only translating a pair of bits, right? So this, I mean, ideally we would like to do it in a 2-bit interval rather than a 4-bit interval.
And so
So this is just an example of construction of an orthogonal family, not necessarily to be used literally in a digital modulation scheme, right? This is not
will
like,
it,
yes,
won't it
please.
have interference? Because as we've said, the one
Okay,
bit pair.
the requirement will be you have to choose ST.
Translation is also 0.
No, before, you have to choose ST such that
Translation
Yeah,
is 0.
ST convolve with its
Own
minus
translated
T.
image
own match filter or something,
will give 0.
it will give 0.
So what I mean is
That's
that
not equal to
the let's say the wave form
That is
transmitted
with-
corresponding to 1 bit pair lasts till 4 bit intervals, whereas after 2 bit intervals another waveform is sent.
Yeah, let me, you will require to choose ST such that these are orthogonal, right? The chip ST should be such that these are orthogonal. If you want to use this method of generating baseband orthogonal waveforms. These are things we have already discussed actually, right? Yes, now coming back to your question, Tarun.
So we see that for 1 bit pair we transmit a waveform which lasts for 4 bit periods. So won't there be interference between corresponding?
I'm not suggesting that you use such a waveform.
Okay.
Right? This is just an example of construction of an orthogonal family. Okay, we will in fact very rarely use this kind of waveforms. One would generate a more efficient orthogonal representation of the bit pattern than the one which I have given in this example. In fact, one can generate MSK-like waveforms in the Emory context, but I will not go into those here, which are more efficient representation than this. I know you may not be very satisfied with this example, but don't take this as an example which is a practical example for use in a digital modulation scheme. Just illustration of the ideas that I have tried to give in this class. Thank you.